All right, welcome to The Explainer. Today, we're going to tackle a really cool concept in AI. How does a computer actually learn to see? We're going to dive into how it looks at a simple color photo and sees something way more than just a flat picture. It actually sees a 3D block of information. And that's the first step to, well, everything else. So let's kick things off with a question that sounds super simple on the surface, right? How does a computer see in full color? But the answer is the secret sauce to understanding how all of modern computer vision really works. To get our heads around this, the very first thing we have to do is kind of flip our own perspective. We need to stop thinking about a digital image like we see it, because for a computer, it is absolutely not just a flat picture. See, a color image isn't a flat thing at all. The best way to think about it is like a stack of three kind of see-through images. You've got one for all the red in the picture, one for all the green, and one for all the blue. So you've got height and width, sure, but you also have this third dimension, depth, and we call that depth channels. Let's look at this block here. It's a perfect example. It might be, say, 6 pixels tall and 6 pixels wide. But notice it's also 3 layers deep. That 3 is everything. That's the red, green, and blue channels we just talked about. That's where all the color lives. Okay, so if the image itself is a 3D block, it kind of makes sense, right? The tool we use to analyze it, to look for stuff like edges or curves, that tool has to be 3D too. You need a 3D tool to work on a 3D object. And that tool has a name. We call it a filter. It's like a little detective's magnifying glass. And just like the image, it has its own height and width. This one's a 3 by 3. But here's the critical part. It also has a depth of 3. And that's not a coincidence. It's designed specifically to match the image it's about to scan. And that leads us to basically the golden rule of this whole operation. It's super simple, but absolutely non-negotiable. The number of channels in the image must match the number of channels in the filter. Our image has 3 channels for R, G, and B. Then our filter has to have 3 channels. No exceptions. All right, so we have our 3D image and our 3D filter. Let's get into the nitty-gritty of how they actually work together. This is the moment where the magic really happens, where the computer starts seeing features. So just imagine this little yellow cube. That's our filter, right? It plops itself down on the top left corner of the bigger image cube, and then it just starts sliding. It moves across the whole image, one little step at a time, looking at a small chunk of the image at every single position. And every time it stops, think about what it's covering. It's sitting on top of a 3 by 3 by 3 piece of the image. You do the math. 3 times 3 times 3. That's 27 numbers. It's looking at exactly 27 values from the image all at once. And at each of these stops, it does the same super simple 4-step dance. 1, it lands. 2, it takes its own 27 numbers and multiplies them with the 27 image numbers right underneath it. 3, it adds up all 27 of those results to get just one number. And 4, it slides over and does the whole thing again and again and again. What's so cool is what comes out at the end of all this. We start with a 3D image, we scan it with our 3D filter, and after all that multiplying and adding, we get a flat 2D grid, a single sheet of numbers. We call this a feature map, and for a good reason. It's literally a map that shows us where the feature our filter was designed to find, like a vertical line, popped up in the original image. Okay, so that's how we can hunt for one specific feature. Pretty neat. But images are complex, right? We need to find lots of things at once. So let's level up and see how this simple idea can be scaled into something way, way more powerful. I mean, think about it. Any single picture has tons of stuff going on. We might need to find vertical lines, sure, but what about horizontal ones, or diagonal ones, or a patch of a certain color? How in the world can we look for all of that at the same time? Well, the solution is actually beautiful in its simplicity. We just use more filters. That's it. We run the same process over and over, but each time with a new filter that's been built to find something different. So check it out. Our first filter, this yellow one, could be our vertical edge detector. It does its thing, slides across the whole image, and boom, it creates this first 4x4 feature map. All the bright spots on that map show where it found a vertical line. And then, at the very same time, we can have a second filter, let's say this orange one, and its job is to find horizontal edges. It runs the exact same scan over the same original image, and it produces its own 4x4 map, this time showing us where all the horizontal lines are. Okay, now for the grand finale. We've got these two separate flat maps, one for vertical lines, one for horizontal. Now let's see how we put them together to create the basic building block of a real neural network. It's actually super straightforward. You take that first map, the one that found the vertical edges, and you take the second map for the horizontal edges, and you just stack them up, one right behind the other.
And this is the big aha moment. Think about what we just did. We started with a 6 by 6 by 3 block, where that 3 was for red, green, and blue. Now we have a new 4 by 4 by 2 block. It's a new 3D volume. But its channels aren't about color anymore. They're more abstract. The two channels now represent how much vertical edge is here and how much horizontal edge is here. We've transformed the information.
And this table just lays out the math for us. You can see the height and width get a little smaller. That's just a side effect of the math. But the most important column is the last one, the new depth, the number of channels in our output. Has nothing to do with the original image's channels. It's all about how many filters we chose to use. So, why did our new volume have a depth of 2? Simple, because we used 2 filters. If we wanted to look for 100 different little features, we'd use 100 different filters, and our output would be a volume with a depth of, you guessed it, 100. You are in complete control of the depth. And that's it. This new 4 by 4 by 2 block, this is our finished product. This is the output of one complete layer in a convolutional neural network. And the coolest part? It's now the perfect input for the next layer, which can take this map of edges and start looking for more complex things, like corners or curves. So we've just put together one layer. It's a pretty basic one. It just finds simple edges. The next layer could take those edges and learn to find corners and curves. And the layer after that could take those corners and curves and learn to find things that look like eyes or a mouth. And that leaves us with a pretty mind-bending question, doesn't it? How many of these layers would you have to stack, one on top of the other, to go from simple edges all the way to recognizing something as complex and nuanced as a human face?